We're now ready to find all the roots for any polynomial, even ones that might have complex roots. So we're going to go ahead and solve the roots for three different polynomials. And to begin with, let's just do a quadratic. So let me go ahead and get this pulled up here. So we're going to solve for x squared minus 4x plus 13. And we'll call this just a polynomial. We'll just call it q of x for quadratic. So in order to find the roots or the zeros or the x-intercepts, however you want to call this, we've done this quite a bit. You set this all equal to 0, and then you have to solve. Now your first attempt should always be to factor. This, however, does not factor. 13 has no factors that add up to -4. So we're going to go with the quadratic formula here. X equals -b plus or minus the square root of b squared minus 4ac, and all of this gets divided by 2a. So let's go ahead and start filling this in. Because this is the first one we've done in a while, I'm going to point out that a equals 1, b equals -4, and then c equals 13. And let's go ahead and start filling everything in. -b is actually going to be +4. We're going to have the square root of -4 squared, and then minus 4 times a times c. All of this gets divided by 2 times a. Let's go a couple more steps along with this, just to try to give you as many steps as I can, at least in this first one. So it's going to be 4 times 13, and then all of this over 2. Continuing along, 16 minus 52 is 36, but it's negative. And at this point, this really is the answer, but it's not in the correct format. It can look quite a bit nicer. So first of all, let's take that square root of -36. Since the square root of 36 is just 6, this is all going to end up equaling 6i. So we would end up with x equals 4 plus or minus 6i over 2. And then distributing the division of 2 to each portion, we end up with 2 plus or minus 3i. And these are our answers. We have two complex solutions, 2 plus 3i, and we also have the complex solution 2 minus 3i. You couldn't graph this, so if you actually try to graph this parabola, it would not cross the x-axis. But at least now we do know there are roots, even though they happen to be complex. Let's do another example, and this one's going to involve a little bit more. We'll have some fractions here. So let's go ahead and say my next polynomial is f of x. It's going to be another quadratic, though. So now we want to find the roots of this polynomial. So once again, setting this equal to 0, we would try to factor first. However, 4 times 17 will not give you any factors that add up to -4. So that leaves us with the quadratic formula. A little bit more work this time. -b is still going to be +4. B squared is 16 because -4 squared. Minus 4 times a times c, all over 2 times a. Now this is a problem I really would do on the calculator. So 16 minus, and then I have 4 times 17. That's something I would plug into the calculator. So plugging that in, I end up with 272. And then 16 minus 272 is 256. Or sorry, -256. So I took all of this and I just plugged that into a calculator. All right. Now 256, off the top of your head, you might not know what its square root is if you're not super familiar. So I'd always just double check on a calculator again. Does the square root of 56 give me an integer solution? So if you plug that into a calculator, you do actually end up with 16. So that tells me that this all can be reduced to 4 plus or minus 16i all over 8. And we could actually take this a step farther, dividing 8 to each of these and reducing some fractions. We should end up with 1/2 plus or minus 2i. And so those are my two solutions right there. So these two examples were both quadratic, and they both dealt with answers that kind of worked out nicely, right? We had integer solutions and fractions. That's what you'll have to look at on Delta Math. Before we end, though, I want to do one more example that's not just quadratic. Let's go ahead and do p of x equals x cubed minus x squared plus 25x minus 25. So here's an example of a problem you could actually start factoring without needing any complex numbers or anything new from this video. So your first step when you have a cubic is to look to see if there's a GCF. There is not a GCF here. So your next step would be to say, well, could I group these? So the GCF in the first one is x squared. The GCF in the second is 25. Let's see what happens. And so since those x minus 1s match, we're in a situation where we can't actually factor. So I end up with x squared plus 25 times x minus 1. So one of my roots is going to be x equals 1. That's a real root. Cool. Now the other one, though, x squared plus 25, well, this is a situation where when I solve, I don't get a real answer. And up until this video, we've said, oh, no real solutions. X equals 0 is the only possible answer. However, we now know that we can take the square root of a negative. And in this case, the square root of 25 is 5, which means the square root of negative 25 is actually 5i. So here are my three solutions. We have x equals 1, x equals positive 5i, and then also x equals negative 5i. And that's going to bring to a close our discussion on complex numbers. In the first videos, you were really just told what you can do with complex numbers, kind of getting a feel for what they are, so it's not just this random thing I'm throwing at you. And then in the next videos, we talked more about how it relates back to what we've been discussing with polynomials.